on H. Okay? Any question about that? Any question about this equation? I did nothing. So this is y, the function of x. So the derivative of this equation with respect to time is indeed y dot partial h partial x x dot, and this is what we call as the derivative. Okay? Any question about that? So we'll start from here. Let's write down the solution of this equation. So it's just y at any time is the initial value of y plus the integral f acting on h. I'll write it as is, but with some detail. So this is f tau x of tau, right? Because f is function of t and x acting on h d tau. Any question about this equation? Initial value plus the integral of whatever you have. The issue is that, we don't know how to do this integral because x varies and we don't know it. You need to solve the differential equation together, right? Any questions so far? So this is for any t, for any time. This is just you can say the definition of the solution of the differential equation. So just for not taking too much time, I will call this guy now on as f tau. So because f is time varying, so this is f evaluated at time tau with x also at time tau. So now I will write again the same thing, y of t equals y of 0 plus the integral of 0 to t f tau acting on h. But I will get this h from, if this is a star, I will get it from a star. Remember, a star is valid for any time t, so please evaluate it at time tau. Okay? So let's evaluate star at time tau. So it's y of 0 again plus 0 to tau. Now we have, and now it's f another tau. So let's please give indices. This is my first tau and this is my second tau acting on h at the second tau, d tau 2, close the red thing, and I have the green d tau 1. Any question about the second equation?
So it's a recursive.
Yep.
Like the Picard theory?
Yeah, very simple. Any question about this? Yeah. And now f tau, this is a vector field acting on a C-infinity function. It's the addition of two functions. Remember, y of 0 is the sloppy notation because y of 0 is h, and then the result I will evaluate it at x0, okay? So this is acting on this guy plus acting on that guy. This is a linear operation, so I'm going to distribute just fine. So I will have y of 0 plus the integral f tau 1 acting on y of 0 d tau 1 plus iterated integral 0t 0 tau 1 f tau 1 acting on f tau 2 acting on h x tau 2, right? d tau 2 d tau 1. So this is actually identity plus the integral of 0t f tau 1 d tau 1. This is all acting on h of x evaluated at x naught plus some remaining term, whatever it is. I don't want to repeat it, it's exactly the same. So this guy comes here. Any question about that? So we have something acting on x naught, but we have a remaining term. So this actually remaining term, still I have h here. I will get it from star again at tau 2 and do the following thing. So you can do this iteration. So at any level you have y of t is identity plus the integral 0t f tau 1 d tau 1 plus yada yada. This is the integral 0t 0 tau 1 0 tau k minus 1. This is the kth term. F tau 1 f tau k d tau k d tau 1. This is all acting on h evaluated at x naught, and the remaining term is also an iterated integral, the next level. So f tau 1, f tau k plus 1, acting on h at x of tau k plus 1. This is d tau k plus 1 up to d tau 1. Okay? And if you take k to infinity, we will get rid of that term. So y of t can be written as identity plus summation k equals 1 to infinity of this kth term. This is all acting. These are all just, what are these? This is a vector field, right? So, and a vector field acting on a vector field, so it's partial this guy, partial the states, times that guy, the result is a vector field. So all these things, and you just integrate them with respect to time, holding the x constant. The summation is a vector field. This will be acting on the function h, and I will evaluate it at x naught. This is nothing but a series solution for your differential equation, which, I don't know, this is 1978. It's very obvious that Naifi and his colleagues in the other track, they were playing with these series solutions for a long time before these results, but from a different spirit and perspective. Okay, there is no iterated integrals, there is no linear derivatives. Okay? Here is more mathematically appealing. Yes?
Why does the last term vanish as we go to infinity?
Because you shrink the, I'm trying to say, you shrink the time. Let's see, so, where is the, okay. When you take k to infinity, so tau 1 is less than, so what is the iterated integral? Tau 1, tau 2. Tau 2 is less than tau 1, right? When you do the iterated integral, tau 2 less than tau 1. Because you integrate d tau 2 from 0 to tau 1.
Okay.
So tau 2 is less than tau 1. Here will be obvious. And this guy. So here tau 2 is less than tau 1, right?
Okay.
So tau 3 is less than tau 2, and so on. So when you go to infinity, you shrink the time interval of the very first integral.
It's not strictly less than, right? It's less than or equal. I mean, all of them can be equal to t in the end, right? Because tau 1 is less than or equal to t. So
You can remove, doesn't matter from the integration point of view of it's a continuous function with respect to time. This requires Lipschitz property with respect to time. It doesn't matter the adding, right? It doesn't matter adding this thing. So you shrink the time interval of the very first thing and it goes away. So you have this exponential representation. So actually, like I said, you can have the h's to be x1 up to xn, and you have this to be indeed x naught, the initial point, multiplying by these guys. So this is partial f, say tau 2 partial x times f tau 1, evaluated at x naught directly, and you get the solution, if you like. Any question about this so far, please?
Professor, identity, that identity, is it a matrix?
No, it's an identity map. So identity acting on h is h. Right?
So that's a vector field, right?
Well,
Because it is being adding with a vector.
you can define a vector field, that's fine, in the sense that vector fields acting on C infinity functions. So this vector field will be the vector field that when it takes a C infinity function, it returns you the same C infinity function, right? this is the identity map, if you like to have it like this. This is identity map. These are not matrices. For if we, when we do, because these are scalars, H is scalar, Y is scalar, but when we do the vector form of it in coordinates, this will be the matrix. Any questions so far? So it seems that this is, between parentheses, this is a good candidate for our goal, right? Remember, we were seeking an operator P such that the solution of this differential equation for y is just P acting linearly on H evaluating at x naught, right? So this is a good candidate for P. So Agrachev and Gemperlitz, they indeed define this to be P. So they define this to be the exponential, right? It looks like an exponential map of this guy. It's just a notation. We don't integrate f and take the exponential. It's just a notation. And they call this the chronological exponential. And it seems that PT is equivalent to this exponential. We don't know yet. We need to show the convergence. Does it converge or not? Right? What are the properties that this series has? And if it converges, does this converge to the solution of the differential equation or what? Okay?